Let's take a look now at some of the physical properties of minerals. And these are the things that geologists will look at when they're in the field. And they will use a little hand lens, which is a magnifying glass. They might try different little on-site experiments to determine what kind of mineral they have. But if it's a little more complicated, then they'll have to take it back to the lab and do a little bit more investigating. Here's a list of some things that geologists will look at: the crystal form, the luster, the color, the streak, the hardness or tenacity, the cleavage and fracture, the specific gravity. We'll even look at the feel, the taste, optical or chemical tests. The most obvious thing when you come across a mineral is its color. This is the first distinguishing feature, but it's not very reliable because so many minerals have variations of their color. And so you might have quartz, for example, that looks very white or sort of clear, and then on another occasion you might see the same quartz that looks very purple. And we know that purple quartz is an amethyst. Quartz also can come into sort of a rosy quartz or a rose-colored quartz, or be smoky as well. So that's why we do write down color and we make note of it, but it's not the unique identifying feature. Crystal form is another property that we look for in the minerals, and this basically gives you the shape of the mineral. It's the overall representation of what that internal structure is doing. A lot of times you might have not a perfect crystal forming. Space might be limited when they initially formed out of the fluids that brought them together, and so they start to overlap. They might grow within each other or against a wall, against other minerals, and so they might take on unusual shapes. But if you are able to find a nice entire crystal, this is the crystal form. Here's an example of a garnet crystal. Now you can see it has very different shapes, and here's an example also where it is growing into other minerals. So sometimes it's really hard to get the overall shape of that mineral, but we can look at different facets or faces of the mineral to try to determine what we're looking at. Here's another example of pyrite, another mineral that also exhibits a variety of faces, and you can see that when it's growing into other minerals it starts to deform, or it's not as pristine, you might say, as an entire crystal. Another property we look at is luster. This is the apparent reflection or the reflectivity or shininess that a mineral might have, and there are pretty much two groups that we deal with, and these are the metallic and non-metallic. And the metallic is a very shiny, reflective luster that tells us we're dealing with a metal of some kind. Galena is a lead compound or mineral that displays a metallic luster. If it's non-metallic, we can also give it names like vitreous, silky, or earthy. And I have a picture here of asbestos. On a large scale, it looks very silky, like long strands, and under a microscope you can see those individual little strands. Streak is a property of minerals that is relatively unique to some, because when you scratch them or rub them against a porcelain plate, sometimes in their powdered form they give a different color. The hardness of a mineral is the resistance of this mineral to abrasion or to scraping. And we have, all the minerals are assigned a certain hardness to a standard scale called the Mohs scale of hardness. And this is a way in which we can compare them to different materials, so that if you're able, for example, to scratch the mineral with your fingernail, then you have something that is less than a hardness of, say, 2.5 or so. And that there are a certain number of minerals or kinds, like gypsum and talc, that will sit below that range. So this starts to help narrow down the range of minerals that you're dealing with. If you have a very tough mineral that not even a knife or a steel nail will scratch, then you're dealing with minerals that are tougher than quartz. So it might be topaz, corundum, maybe even diamond. Our scale goes from a 1 for talc, which is the softest mineral, all the way up to 10, which is our diamond, and that's our toughest or hardest mineral. Cleavage is the tendency of that mineral to break along a plane of weakness. Now, generally, the cleavage coincides with the orientation of some of those crystal faces that we saw earlier. There are prescribed geometric shapes for every mineral. There's a certain number of planes and angles between those planes for each of these cleavage assignments. So let's take a look, because that's always the easiest way to look at and understand cleavage. Here's an example of a calcite crystal, calcium carbonate, and the way the atoms stack up gives us a rhombohedron. Looks like a cube that has been slightly stretched. When you start to look at the cleavage, or the possible number of planes that you can get when you break this mineral, there are 3 different orientations. They can be either greater or less than 90 degrees from one another. So we have a number of them. We have cubic, we have rhombohedrons, we have octahedrons. There are many different cleavage planes for different groups of minerals. Fracture is another property of some minerals. Some of these, if you fracture them, will not break on a very nice plane. They literally break apart, and so they could have very irregular shapes, or we can have something that we call conchoidal fracture. Conchoidal looks like smooth and rounded surfaces, and if you look at glass or obsidian, and when you break it, it will have a conchoidal type of fracture. Geologists will also look at the specific gravity. This term assigns or talks about the weight of the mineral and the weight relative to water. So if we assign water as a reference, a specific gravity of 1, then some other mineral will be, say, twice as heavy as the same volume of water. In general, the average specific gravity of minerals is somewhere between 2.5 and 3. As I mentioned before, there's a lot of different properties. When we have so many minerals in the field and you're trying to identify them and there's some similar properties between them, we basically try to grab anything we can.
This might include fluorescence. Does it glow in the presence of ultraviolet light?
Does it react with hydrochloric acid? We have what we call the fizz test. We can show that fizzing reaction when we put hydrochloric acid on some minerals. Is it flexible or malleable? Sometimes you can sort of bend minerals. Are there optical characteristics, reflective properties or refractive properties? Does it smell or taste funny? I wouldn't recommend tasting minerals, but you can definitely smell sulfur compared to other minerals. And elasticity. And there may be other properties as well that are not on this list. Now, one of the final things I want to talk about with regard to the first impression we get from our minerals is, are they large crystals, small crystals, or glassy? If they're large crystals, this tells us something about when it was formed, the cooling history. Did it cool slowly? If so, it had time for all the atoms to aggregate and the molecules to aggregate into a large crystal. If it cooled quickly, there wasn't that much time, so your crystals tend to be smaller. If the magma or the initial melt cooled very quickly, almost instantaneously, that's when we get glass. That's when we get the obsidian and the very, very fine material where you really see no crystal structure. Now, when you encounter a mineral in the field and you can't identify it, generally we bring it back to the laboratory and we create what we call a thin section, where the mineral is polished and sliced down to a little sliver that's about a micron thick. And we can stick this under a microscope and look at the optical properties. And when we do put a mineral or a rock under the microscope, you can see very small or tiny little minerals, and this requires now some optical properties that we won't cover here. But there's a whole field of optical mineralogy that'll help you identify minerals under the microscope.